Welcome. My name is Jeff Crandall. I'm the senior manager for additive technologies here. I've been working with additive manufacturing here at CCAT for the last 12 years. So we're involved in the whole conversation. We're involved with plastic, we're involved with metals, we're involved with continuous carbon fiber. So we're involved in many different aspects of additive. So a little bit about us. We're a not-for-profit, to answer your question. And so I'm going to talk a lot more about what programs we have available to you. But basically, let me just show you here. Here. For the slides. So this is our agenda for the day. One of the things is that I don't want to wait till the end for a Q&A session. So I'd rather let's stop. If you have a question, answer it. Have a conversation. If you've got something from your experience, I don't know where you guys are at with adopting or having used AM or whatever the processes are that you're using. If you want to inject something, just go right ahead. It'll be a lot more fun if it's a conversation than if you just listen to me Latin for the next hour. The logistics of the space when you're out on the floor, we don't want photography out there. Some of the stuff we're working on might be company proprietary for individual companies. We do high-tower work as well, and so we'd rather not that. Restrooms are literally downstairs in the big machine control room. So help yourselves. Don't wait for a break. If there is a emergency, we'll go out through the front door and head over here to the flagpole, which will lead you on the way. And then last but not least, at the end, they will send you a survey. So we really appreciate any feedback that you can give us on that. So here again, you asked what we do for a living. We work with manufacturing companies to try to introduce new technologies. A lot of times new technologies are risky and it takes an understanding of it before you make the investment and all that. So part of our job is to de-risk technology adoption. We have, and we'll talk a little bit more about it, but we have funding sources from the state, we have funding sources on a federal level, and we do what we call commercial work for companies. So if you're a large company, if you're out of state company, we do work on a commercial basis. For the state related money, our focus is primarily with mid to small size manufacturers. But it's really, so you can come here, we could talk about, I'm interested in adopting additive, and I'd like to, this is what I make for a living, how can additive, how can I benefit from additive? Or can I benefit from additive? Or are there parts of my manufacturing process that might make sense to interject something that was made additively? So we can help you with that. We have funding to do a small demonstration project. We can build a widget for you and let you try it out and see if it makes sense. So it's really to demonstrate and validate what those technologies are to help you understand it and if it makes sense to adopt it. So it's really we're an economic development entity that's using technology to try to benefit manufacturers in the state, in the region, in the U.S. So these are some of the people that we work with. So we work with literally small to mid-size manufacturers. We work with the big OEMs. We work with government. So we do a lot of work with you'll see a Navy project. I'll talk about an Air Force project, some of the national labs, and we work with universities. So a wide range of kinds of work that we do and people that we work with. And so here again, looking out the window is our Adam lab, so that's from the other end of the room, so you can see a bit more of the equipment that's in there. And the other lab that's in this building is my lab, is the Atom lab. So they're going to talk more about what's in here. But when you look in this photo and actually combine some of the stuff that's over there, we have 10 different machines in there, and 8 of them are 3D printers. So we have Pod Mini Mill and Mazak Variax. These are the only subtractive machines that we have in there. We'll talk more about the DMG, which is kind of both. We also have we have another lab over at Goodwin University that deals with composites. So it's a collaborative between Goodwin University, Pratt and Whitney, and CCAT and the state. So we're here today to talk about additives. So once again, some of the processes involved, some of the types of equipment that we have here. So we're going to talk about what is additive. So before I go any further into that, so who in here uses additive already or has used it?
In our tech schools, we have for the last 5 years anyway.
Okay. All right. You go.
I work in consulting, and a client that I work with is applying it to their process and looking to scale.
Okay. So it's something that is pretty prevalent. The technology that's pretty prevalent. We're going to beat that to death before we get done with it, but it's good to see that people are using it. So what is it? It's an industry 4.0 technology that uses a CAD model, computer model, to build a part one layer at a time. It adds material where it's needed. So that's how I define it. There's probably other definitions of it, but that's basically it. What we're going to do is compare that against traditional manufacturing processes. So that's what a lot of folks are involved with. So, traditional manufacturing is a huge family of different technologies and different processes. Injection molding, casting, forging, stamping. There's some examples of it. Machining or subtractive, milling, grinding, turning. So these are all things that remove material from a feedstock. So when you look at these processes, we're going to look at subtractive manufacturing and milling in this case. You start with a 3D CAD model. So it's a digital process nowadays for the most part. The only thing I can operate, unfortunately, is a manual milling machine. So give me a bridge for it. But so anyway, you generate a tool path. So you can do your development, you develop a tool path. You look at what tools you have available, what the processes are in order to design the process for it. You take a block material and you remove what you don't want. So pretty good process. So that's the way high precision parts are made today. And that's the way a lot of parts are made today. And that's the way we've made really great things for the last 200 or so years. So since the first industrial revolution, these kind of technologies have been, prominent technologies. One of the issues with it is that you can create a lot of waste material. So we've done projects on our milling machine where we were making a handful of aluminum parts for the company. And I don't know, I think we ended up with, for us, it's a lot, like 6 55-gallon barrels of aluminum scrap. So when you consider we were making 20 parts, that was quite a bit of scrap. There's potential for long lead items. So if you are making something, if you're finishing a casting or forging or whatever, your process may be relatively short, but you can wait weeks or even years in some cases for casting or forging it. So we've got a couple of projects that we're working now that are trying to deal with lead time and things like that. We'll talk more about. You design for manufacturability of the process. So any manufacturing process that you have, you need to design for that process. So whether it be additive or whether it be subtractive. But a lot of times in subtractive, you can only remove where you can get your tool into. So you have to make choices between the ultimate design for performance and design to actually build the part, right? That's pretty common. So, so at times you have to sacrifice performance or potentially might have to, or some other aspect of the finished part in order to actually build it. And it's a part of this process. And typically, the more complex the part is, the more complex the part geometries or whatever, it takes longer and it's more difficult to machine. Is that an accurate statement? Okay. So that's the nature of the beast. The more fixture setups you got possibly or whatever, just becomes more complex. Whoops. Now we're going to compare that with additive. So additive starts with basically the same pattern model. We might have to modify it because here again, we want to design for the process, but it starts with this CAD model. They use programs called slicing programs to do the CAM to generate the tool path. And then that controls your deposition and you add material layer by layer where it's needed. So it's a complete opposite view of how to build from subtractive. Results, so it allows you to make things that can be difficult or impossible to do with some of the other technologies. As an example, complex internal features. So those are difficult to do with the conventional process. In many applications, and this is one of the key sentences for this whole thing, is that additive tools can be applied to reduce the manufacturing cost, improve product performance, reduce design and manufacturing lead times, and enhance maintenance, repair, and overhaul and spare parts availability. So that's the parts of why people are looking at going for additive manufacturing. And we'll probably talk about this multiple times as well, but there was so much hype around additive manufacturing when it first started coming out and about. And so, it was going to do everything. It was going to replace conventional manufacturing. And the world was going to be a better place because of it. And it's not the case. Additive is simply, it's another set of tools that are available when you want to make something. So there's times that additive tools make an immense amount of sense. There's times when they make no sense whatsoever. It's harder, more expensive, and to use that technology than conventional processes. So it's just another tool, and you have to pick and choose when you can use it. When we looked at subtractive, here again, there's a lot of traditional manufacturing processes. The ASTM Standards Organization has defined what these additive families are. So there's actually there's 7 additive families plus hybrid. So hybrid is just simply a combination of technologies. Typically, it's a subtractive technology and additive technology combined in one machine. But these are the different families of additive technology. We're going to talk more about those here in a couple minutes. What can you make with additive? Anything and everything. So, most people, when they think of additive, think of using plastics. So that's what, this guy's for. I've got a bunch of parts up there. Nylon is a very common material in composites. So, so this guy is nylon with chopped carbon fiber in it. So this is, you can do continuous fiber or you can do with chopped fiber in it, but that's adds stiffness to it. So that's a really nice material. So additive materials, the plastics, they've been doing additive plastics since the 1980s. And so there's a whole bunch of traditional and now some higher grade materials that are available for plastics. So full range from engineering grade plastics to flexible plastics, inexpensive PLA, which is made from basically corn to ABS, just a whole range of plastics. Metals, same thing. A lot of the machines you will be looking at when we go down there use a heat source, a laser beam. They can use an E-beam, Mars use lasers for a traditional welding process. And so the idea of melting metal, basically welding in a very precise, controlled manner, has been around once again since the 1980s for all intents and purposes. If you can weld it, you can probably use it as a feedstock. If you can't weld it, there's some possibility that it might work with additive. It is like, we'll say this more than once as well. There are welding processes, there's lasers that are used, or basically laser welding or MIG welding, TIG welding, whatever. It uses that technology, but welding is not additive manufacturing. And so there's some differences that come in there. Biological materials and pharmaceuticals, so they're printing cells, living cells. They're printing medicine. So I was talking to a company the other day that's making custom pills, basically, that can layer and all the medications that a person might want. I use my dad as an example. Later in his life, he would take handfuls of pills during the day and having the time right and all of that. They're getting to the point now where they can custom make pharmaceuticals that he would take one pill or maybe 2 pills a day. They have all the primary release aspects of it, all the pills in one tablet. So it's kind of a revolutionary idea. Concrete and building materials, when you use additive in construction, it's called contour crafting. And so, there's an example. This is a wall being constructed. So you kind of have this big extruder extruding icing, cookie or cake or whatever. These are some houses that were built from it. This was in Mexico, but these are built in a seismic area. These are low income housing. So there's a lot of people that are looking at this as a construction method because you can use local materials. You come in and either, erect a giant robot or a giant gantry system, and you can build, the walls in a fraction of the time that you can traditionally. So the idea of building low cost housing, the idea of going in where there's been some kind of a natural disaster and rebuilding houses quickly and reasonably local materials is something that they're looking at. NASA is looking at this as the way to build structures on the moon and on Mars and using the regular the local soil and material that's available. Food, here again, a couple of examples of food. If it's hard to do conventionally, this might be an application for it. So once again, just very intricate part geometry. Electronics, they have liquid metals that they can spray on or apply to a material. They can put it on cloth actually and do in situ smart clothing with sensors built into it. And they're looking at that from a military perspective to, a soldier to monitor your health and well-being. They print antennas on, UAVs and there's just a million things. If you have a cell phone and you are they probably used a additive process for creating the antennas inside. Ceramics, you can print a wide range of ceramics. So here's a ceramic piece that was 3D printed. And then new materials. So once again, the material side of it is evolving very quickly. And so, there's people that can custom make a metal alloy for you. You tell it what the performance characteristics are that you need, and they can create an alloy. They're fine tuning existing materials. So there's a lot of work going on in materials. All right, so why are people using it? Once again, we talked about the potential to make things faster, cheaper, lighter. This is an example, and there's a part in the middle there. This uses topology optimization, so this is actually a bracket for a concept car, an electric concept car. And this weighs about 60% of a bracket that's manufactured traditionally by using these organic shapes. Here's an example of, I think this is Airbus related, where traditionally manufactured bracket and the manufactured bracket. Create things that are difficult or impossible with other technologies. Once again, we have, and this is kind of the part consolidation. So this was printed from liquid metals, but all of these gears are integral to this system. So this is part consolidation, but it's something that would be difficult to use with other technologies. Part consolidation, this is a GE nozzle for the LEAP engine. And that started like this 24, I think, individual parts that were traditionally manufactured. That means you've got multiple suppliers, you've got to manage, and the logistics of that has to be assembled. They started building these things additively as a single piece, and then you're going to finish the parts that need to be finished. But the last I knew, they had 6,000 or 7,000 of those that they had manufactured. So part consolidation. The ring is we'll see it when we go out to the shop floor. Is basically a casing. This hasn't been finished on the inside or outside. That started life as a flat build plate, and the engineer that built this built the flange, and then we built the wall and flipped it over 90 degrees, built this flange, machined it, and then he added the washes on it and machined those. And oh, by the way, this is stainless steel, that's bronze. So, and that whole thing was built from absolutely nothing to that level of finish in 8 hours. So you could probably do much better than that if you had a casting that somebody brought into you and then you finished machining. But if you wanted to build that and you didn't have a casting, have that part in your hand in 8 hours is huge. Design or spare parts potentially. So there's a lot of applications where that's a much faster way of going. There's typically no tooling or fixtures. Well, hello there.
Hey,
How's it going?
good.
Good. So there's typically no tooling or fixtures involved. A lot of times when you're building, you build in your own support structures. So you don't need external fixtures per se. Once again, designed for end use versus manufacturer. So if you look at this, here in the middle of this lattice work structure, that really didn't take any more time to build and was no more difficult to build than if that was just building a solid block. So it's a very simple thing to do. When you look at design for end use, here again on the far left is part of a heat exchanger where that was all built as a single part. Free complexity once again, and then very little waste. So I'm part of. So when we look at these parts, once again, we kind of hand some of these around to have something here. Start here, right? So you can see the level of complexity of a part that you could build, and I don't know how you would build that conventionally. So to me, that's a part that can only be built using additive. The shoes up here, Nike and Reebok in particular, are doing a lot of work with high-end shoes being printed. And if you look at the NFL helmets and things, they have that kind of a matrix built into them now to protect the players' heads. And a lot of that is being done with additive manufacturing. So key points. it's rapidly evolving as a mainstream manufacturing tool. It's a subset of tools which we talk about, so it's just another set of tools in toolbox. And as we said, it's a family of technologies. Some of them are really good at some things, others are better at other things, just like milling is great at some things, turning is great at others. It's just, there's a lot of variety available. So a quick industry overview. Any questions? Okay. So the additive industry as a whole, and metal additive in particular, is growing at 9 times faster than traditional manufacturing. When you look at that and say, "Oh my God," but when you look at worldwide manufacturing, additive manufacturing is still less than 1% of manufacturing, so it still is a tiny entity compared to traditional processes, but it's growing faster. So hybrid, here again, specifically in relation to metals, hybrid is growing fastest of metal technologies. We're going to talk a lot about hybrid here in a minute. And there's a lot of powerful new technologies emerging. So we're going to talk more about that. But the bottom line is that as people understand what additive can and can't do, as the technology and the equipment matures and people figure out how to do things better, there's just a lot of growth in the types of equipment. There's a lot of growth in kinds of technologies that are available to you. So these are just some random trends. So refinement of existing equipment and processes. So everything that they're machines. So the first generation machines were pretty much made by companies that said, "Hey, additive is really cool. If I build a machine that can do this and this and this, I can create something additively." But they were additive companies, and so a lot of traditional equipment manufacturers have realized that additive is up and coming and want to get into the game. So when you look at DMG or Puma, Mazak, Haas, when you look at Trump, you look at a lot of different manufacturers, they went out and actually bought these first generation machines. And so the next generation machines are ones that these machine tool manufacturers that understand building robust machine tools have made. So the next generation machines are much better. So as an example, we had a first generation machine that was bought by Renisha. So we bought the first gen, which is basically the same machine that the manufacturer that they bought, and it had no sensor or ability to gather data. That means that from the quality control perspective, you don't have a lot of information to tell you about what you're building. So a lot of the old machines were prone to issues with robustness. They would break down. They were difficult machines to deal with. The newer machines are much more robust. They're focused on a production environment. So when you look at the older machines, particularly we'll talk about the laser-based ones, the machine had one laser in it, and it had to melt everything you wanted to melt on a layer. Now they're making machines with 2, 4, 8, even 16 lasers, so that they're able to go much faster than they were before. So it cuts it down to a fraction of the time to build a part. Laser wavelength choices, not important for this conversation, but not lasers come in a wide variety of different colors. And some of those colors interact better with metals and get absorbed by metals more. So it just gives you more options depending on the kinds of materials that you're trying to process. And then evolution and refinement of the processes themselves. So here again, how to make those machines do the things that you really need them to do and has really come a long way. So once again, most of the next generation machines that are available today are certainly much more robust production oriented machines than they were 5 years ago. Another industry trend, and I actually I'm going to change this. So printing bigger or printing smaller. So one of the machines, a machine that made that hinge has a 10-inch by 10-inch by 10-inch work line. So you can build anything you want to within that 10-inch cube. They're actually building bicycles in that and then assembling the individual components to make titanium mountain bikes, as an example. But the idea of printing something bigger than a basketball is huge. So there's a lot of different manufacturers that are making equipment that are designed to build at a much larger scale. You can build a much larger part, or you can build more of bigger volume of parts simultaneously to speed up the process there again. So we were talking to an engine airframe aerospace manufacturer just actually earlier today, and they have some parts that they want to do that are traditionally done on a machine that has the size of a basketball. They're printing meter wide parts, so engine casings for that in particular. They're also going the other way around, so they're making things on a nano level that they haven't been able to do before. So it's really kind of cool. And so both in the HRAM, so high rate additive manufacturing technologies and systems. So one of the things we'll look at when we go downstairs is we call it our flex cell. It's a high rate deposition cell. It's a robot based welder. And so we can put down 10, 12 pounds of material per hour, which is a fast build rate for additive manufacturing. We can do in hours what will take days or weeks in some of the other machines. So it's really good. Standards and qualifications. So everybody says, everyone is aware that it builds anything that you have to respect it. You have to be able to, it has to meet your quality standards. It has to meet whatever specifications your customers have. And so even though additive manufacturing has been around since the 1980s, it's still considered a new guy on the block. So they've been casting for what, 5,000 years, something like that. So people are very comfortable with casting because it's a tried and true process that's been around for a long time. Here again, people are very comfortable with raw materials and forgings and those kinds of things. They really are conservative in how they look at additively manufactured parts. It's not a casting in the traditional sense, not a forging in the traditional sense. It's not raw in the traditional sense. How does it relate to all these things that the existing standards cover? So what is taking place as an industry is that all these different standards organizations are working really, really hard to create standards for additive that will let them inspect and do to these standards so that it becomes a more acceptable process. So when you look at the aerospace as an example, the FAA is very actively looking at how do we qualify additive manufactured parts. And so there's just a lot of that type of thing that's taking place. So we talked a little bit about the wide variety of materials. We talked a little bit about fine tuning, but there is a lot of work that's taking place in this from the materials perspective. So if you're casting, that's a relatively slow cooling process. If you're melting something with a laser beam, you're creating a liquid metal that cools within about 1,000 seconds. You have a very rapid cooling rate compared to a casting. It creates something that might be equal to a casting as far as mechanical ability, capabilities, but it's different. So they're finding out if we add this little bit of additive, or we take away a little bit of this alloy in this, or this metal in this alloy, that now they're getting the same or similar results. So there's a whole bunch of work on the materials and things. And we talked about the plastics, with some of the new engineering grade plastics can compete with aluminum in particular as far as the aluminum goes. And it's lighter in weight. So there's a lot of things going on. So what are they using it for? Prototypes and models. So additive originally was known as a prototyping technology, and it's still one of the primary uses for it. You can build something quickly and easily. You can use models to help understand a more complex part. So here again, we've heard of machine shops that if they have a complex part coming in, they'll build a plastic model with their printer to see how to fixture it, what it looks like, and then they'll get it figured out before the part arrives. Aids to manufacturing. So this is a fixture that we built for a company. So I love this thing. So that's a big part. We're going to talk more about all these as we go on, but bridge parts and repair. So a lot of times when you talk about a repair, somebody wants something that's qualified and meets all the specifications of the original part. And that's great, and that makes a lot of sense for making a permanent repair. But what if I just need to get my Humvee back to base, or my helicopter back to base, or whatever? Can I use a bridge part to get me where I need to go that doesn't need to be fully qualified? So people are starting to have that conversation there. Replace castings and forgings or assisting casting processes. So once again, there's a huge effort. The casting industry is right now seems to be suffering from problems with lead time and quality. And so whether we're talking about shipbuilding, or we're talking about aerospace, that seems to be a common problem. So can we build something that replaces it until the casting that we ordered comes in, or they're actually using additive processes to help the casting process? So I can build a part. I need a casting of this made. I can build a plastic part, use this as a pattern, or I can take a sand printer and add the sand printer, like Yankee Casting has up in Enfield, and I can actually digitally print a mold. And so, that's a much faster, easier way of doing it. And they also, believe it or not, they make end-use parts for it. So parts that actually go into use. So this is a key concept as well. So there was a lot of hype. There's been a lot of fear about additive, and it's waning. And the reality of what you can and can't do with it well are starting to come to the forefront. So people are understanding more how to take advantage of it, how to use it, when to use it, when not to use it. So that's why it's really starting, I think, to advance very quickly as a traditional tool, or as a tool. So I was at a conference last month, and it was a conference that was about additive manufacturing. So the people there obviously had a vested interest. The people there, half of them were doing additive, the other half were just exploring it. So, but when they asked people, how are you using it, 35% were actually making end-use parts with it. So that's huge in my mind. 15% were making tools for others, 45% were using it for doing internal tooling, and 68% were using it for prototyping. So here again, it's a very common application for it. Of those people, almost 70% or 70% said that they're using the in-house capability. So they have printers in their business. 18% farm out their work entirely, and another 12% do a combination thereof. And here again, they're Their thing was additive is production without cooling. And so that was, I think, a great concept. So end use parts. So once again, a wide variety of applications. These are just some quick samples of stuff. But from the aerospace industry, clothes and colors, medical industry. This actually is the part we built, we'll talk more about for the nuclear power industry, oil and gas. All these industries are using it to build and use parts. Okay. Aids to manufacturing, so fixtures, jigs, assemblies, anything that you need is made for manufacturing. So I'll pass this around, but I love this. So this was a fixture for a company that makes electrical cables. They wanted a method for stripping insulation off the end of the cable. And so one of our interns actually built this fixture. He designed it and he printed it. It took overnight to print it. But that has about $1 worth of material on it. And so the question is, how would you build that conventionally? And how long would it take you to have something like that made? So, and the thing of it, it was an absolute failure. Did not work for teams. So could you imagine if you paid somebody to, I'm just picking a number, but 8 weeks to machine that out of a piece of aluminum for you to find out that it didn't fail. So, versus $1 and then get go and come back the next day and there it is. So it's a really cool example of it. So that's part of the design process, dramatically reduce development times. So I love these. So you guys know what this art is? It's face shields from the pandemic. And so the problem with the pandemic is that everything that made things like this was overseas. And the overseas supply lines were dramatically screwed up. And so they turned to people, thousands of people across the country, thousands of printers to start printing PPE, so face shields and masks and that kind of stuff. So, and the federal government had a website where you could go and get the latest CAT file, the STL files that you needed to print this. You could print this and then give them to your local, hospital or EMTs or whatever. So the first design that came out with, the thing was kind of big and clunky. This took forever to print. So very quickly, they realized that there were probably other better ways to do this. So they redesigned it and they sent out the next iteration. So people started printing this guy. So same function, holds your face shield, but they didn't like this. So what they would do is print these out. People in the field would put them to use and make use of them. Then they would get feedback as to, does this design work? What do we need to do different? What they didn't like about this was that it was much faster to print, but it was open at the top. So airflow across the front of the face. So then they came out with the next iteration. So the bottom line is that, additive allowed people in a distributed fashion to make these things, get them in the hands of people that needed them, try them out, find out what worked and what didn't work, how to make it better, redesign it and redeploy it. So all that could take place before they had time to make the molds to do these injection molding, which is the way to do it. So, but it's a really neat application where additive plays an interesting role. 21st century duct tape. So there's people that get their first printer and then they end up doing anything and everything with it. So once again, I can use them as an example. So these two pieces are critical to my little cell bed. And so this was the end cap for my mast, and this was actually for part of the water system. But, so quick and easy.
Yeah, did you design those yourself? Did you pick up schematics?
Actually, I have to admit, the cap I did design myself. That's the extent of my design skills. The other one is much more complex design wise, and that was done by a guy that's our NX master.
You get printers pretty cheap. I got one at my house.
Yeah.
$100.
Yeah.
$100?
Yeah. Well, it was on sale. It's $200 printer, but you get it for
An
$100.
Eigler?
Micros. And yeah, and
Edler. Those are great printers. We had out here for quite a while.
Micro Center does deals on them. You can get them for $100 every couple months.
They can't go wrong. You can throw it away. You don't like it. So wide variety of materials, once again, some of the parts, like we have a part forge down there, I'm not sure about the others, but you can stop in the middle of a plastic build and add metal inserts and then keep going. It's cost effective. We've done a number of molds for companies, either for short run injection molding or just for pouring urethane or silicone in or whatever. And so easy design mods and put numbers in. So we've seen these actually used at customer sites that are where they've made fixturing or whatever in their process. They put a serial number on it so that they can track it in their quality system, and so they just print all that in one time. This is a robot gripper, which this is a great application for it. This is a polymer, so it's nice and lightweight, and then this is actually an additively manufactured tip for it, so you can wear out the tip, you just switch out the tip. MRO, so we talked about repair. So this is a casting. This is for Lord Leonard in the state. So this was a high dollar value casting. Somebody crashed their head into it. So we machined away the material and then deposited fresh material on it so they could reclaim it. That's a big part of it. Unavailability and legacy parts here again. We've done a lot of work for the Air Force. I think we might have a slide in here, but bottom line is we've done a lot of work like with the TF-33 engine. The last new one was built in 1969. So they make some new parts for it, but most of the stuff ends up getting repaired. And so the Air Force is looking at this kind of technology, 21st century technology, to help them do repairs easier and quicker. So we can do in a matter of actually literally a few minutes what takes them hours to do conventional. So they're very much looking forward to it. And then we talked about the parts. So case study, DoD. So the Department of Defense is incredibly interested in using AM for this kind of application. They have a bunch of systems that are old. They need to keep them alive and running. And so, people stop making new parts for them. Manufacturers have gone out of business. They need a small handful of parts in a year's time, and nobody wants to make a small number for them. So a lot of times they get no bids on spare parts. And so the ability to have parts that they can, technology that they can more quickly and easily make parts with. They're spending a lot of effort on this. The idea of warfighter to depot level support. So they have pods basically that they can drop off at the front. They have some with a lot of them with conventional milling machines and stuff in them, so you can do repairs on site to get your whatever back to the depot or get your cannon shooting again or whatever. But they're also deploying additive technology to the front as well, with the same ideas in mind. And they're saying since World War I, basically, we've had pretty open access to our supply chain. So even though we had submarines blasting our supply ships out of the water, most of it got through it. But in the future, they're concerned about our ability to keep a supply chain going, you know, a contested, they call it supply chain. So the idea of being able to make parts where they need them, when they need them, is an important part of their policies and processes going forward. So once again, machines have been around for a long while. They're changing, they're getting better. Materials are getting better, and so are the advanced tools. So here again, we looked at the sample lightweighting, the ability to use generative design or topology optimization to lightweight. These design tools can help you consolidate parts. We talked about GE's LEAP engine nozzle, but they have a engine that they're working on that they've taken, I don't know how many parts are in the engine altogether, but they've taken 812 parts, I think it is, and condensed them into more complex assemblies. So now they have 12 assemblies instead of 812 discrete parts. And here again, they have to use this kind of technology to do that. Yeah, most of this we talked about. It's not going to replace traditional manufacturing, but it has potential of being disruptive in many applications. Bottom line is good too. So many of the parts need to be finished using traditional processes. Anything that we make in metals, or almost anything that we make in metals, if surface finish or dimensions are critical, you're still going to have to probably do some kind of post processing. So traditional manufacturing may shift into supporting this, and and it's more of a finishing process than a roughing process. In fact, a lot of additive companies that sprung up just to do additive manufacturing have actually bought machine shops in order to do that. And some machine shops have adopted additive manufacturing technology so that they have both available in a single place. And that's a really powerful business thing. It's here to stay, it's not going away. It is evolving and being adopted much faster than many people realize. Here again, we talked about the designs for additive manufacturing, design tools are changing as well. We talked about qualification. But to me, this is important. Every major corporation. So if we look at this area, obviously aerospace and medical are big, but every major corporation in the world, for all intents and purposes, every state in the U.S. And every industrialized nation in the world wants to be leader in additive manufacturing. So when you look at what's taking place in China, Japan, and in the European countries, even in some South American countries, there's a great emphasis on additive and bringing that technology to them. Dubai and the Arab Emirates is said, they understand oil has there's a tombstone sometime in the future where oil's not going to give them the money, so they're looking for us an alternative. They're investing a lot of money in additive manufacturing, and they're investing a lot of money in contract crafting. So they have some high-end, amazing structure. Excuse me, they've created with it. All right, so everybody all right? Right, I've got probably a lot more slides than I have time. We'll take a quick look. Most people that start in AM start in plastics. It's the easiest. It's your $100 printer. And so here again, when we looked at that family of technologies, their official name, but there's what they are. So we're going to take a quick look. This is the most prevalent technology. So material extrusion filament printer. So your Endler or a million other different type printers. You can buy material here again that's a few dollars a spool that's made from corn basically to several $100s a spool that are engineering grade materials. So wide range materials. So this is one of our printers. This is the guy that's downstairs here, our forge. This is a Prusa. Yeah, when that was new, I think it was $1,000 printer. It's really what it did. What?
I just bought one of those to work too.
Oh, did you? Good. So this is actually a model that we printed. This is an aircraft fuel component from an antique aircraft. So we actually scan this in with our 3D scanners and then print it part on that. This is a part made from Alta. So this is part of a duct system. This is as strong as aluminum, of a fraction of the weight. This is a fixture that we made here again. It's got a curved surface. I'll show you the part that this held. But once again, how would you manufacture that? You know, how long would it take you to machine it? I guess would be the bottom line. It's probably the other way you do it. So a lot of reasons. Resin printers, SLA, stereolithography. This is probably the oldest of the plastic processes. You can make really great parts with it. Once again, a wide variety of materials. You start with a vat of resin, and the part is dipped in it. There's a UV light source. It can be a laser, it can be a display screen. It cures it, it pulls it out of the resin, dips it back in, and so when this hand was built, it was actually upside down, suspended from this framework up here. When it pulls it up out of the resin, it's cool. So you know, it's this usually when you get done with it, you need to clean the resin off of it. So you usually go into a bath of alcohol or some other appropriate solvent, and then you treat it with a UV light and make sure that it's fully cured. But once again, the level of detail on this, some people that do fixtures like this prefer this technology. Here again, you get the materials range from a wide variety of traditional plastics to flexible materials, keeping and things like that. So depending on what you're doing, this may be a alternative. We can talk more about that individually. Material jetting. So this is traditionally thought of, I think, more of a manufacturing process rather than like a prototyping tool. I don't know any shops that have one of these. I know service providers that sell parts from these for a living, but in this particular case, what we do is the material that's jetted is the actual build material. So it's a plastic, the polymer, and then it's UV cured, and it adds another layer. So it sprays material where it's needed in order to create the part. The beauty of this is that you've got multiple colors available, and you have multiple thermometer of materials available. So like this kidney model here is printed clear, but the vascular system is printed in red or blue, artery or vein. Doctors use this a lot of times for building models of complex surgeries. So they'll take your CAT scan and they'll build a model from it, and it helps them visualize what they need to do during the surgery itself. They can also use it for sometimes for building custom tools that can help them in the surgery, and they build those a lot of times. Excuse me, using the additive as well. But you can also change durometers, so you can mix materials that are flexible and ones that are stiff, and you can vary the mixture to create different durometer levels. And actually, there's a medical, we're studying that to make models for doctors to actually practice the surgery on. So each of your tissues has a different sponginess, and they've actually explored how do we make a model and vary the durometer of the materials to equal what the real tissue is, so that they get to look and feel doing an actual surgery. So, interesting. And powder bed fusion, so selective laser sintering. Most of these, well, there's a number of plastics and materials that they use. I'm not sure if that's one of the nylon ones, but you start with a bed and a plastic powder, and then in this case a laser beam actually writes across it, and it melts that layer, drops down, spreads a layer, melts it, drops down, spreads a layer. So particularly with the nylon materials, you can create incredibly robust parts with this. So a lot of people are using it for end use production. So Each of these machines, there's a bunch of different manufacturers for them, different sizes, different features. And go over. Any questions on the polymers? That was kind of a quick dive. All right, on the metal side, once again, these are the families. Some of them are sinter based. We'll talk more about that. Some of them use a heat source to actually melt the powder. So typically a laser or an electron beam. And some of them don't melt anything. The solid state process is an good thing. Found metal. So we have, actually, when you go out in the lab, we'll take a look at it. Found metal is starts with a filament typically, or a rod. Some of them use a slurry or a liquid, but with the ones that use a rod or a filament, it looks like a plastic printer. And so it's using the same technology, except that the filament is waxy polymer, but it's impregnated and filled with metal powder. So you're actually building a part that you then end up debonding and then sintering to solidify. So this is an example made from copper. This has a part built into it, but this is a heat exchanger. So that took a few hours to make, and then had to go through the sintering process, which is I think a 2 or 3 day process. And then they create in between, you can see here this white. This is the boundary layer, and they use a ceramic material on that, and it lets you just snap it off. So you don't really have any big problems with support removal and things like some of the other processes. This is a part that was made with it. It's a little Chinese dragon. So you see those all the time. People build them on their printers out of plastic, but to be made out of copper with that level of detail just blows my mind. So we'll take a look at the process real quick. Like, so this is desktop metal system. So instead of a filament, they use a rod. And so you print it with a printer here again. It's just like a filament printer, builds a part, and then you end up with results similar to MIM. So that's an important thing to know. The rods come in common materials. So I think comes in 17.4 or 625. You know, I think a tool steel. I'm not sure which tool steel. Many different common materials. And here again, we talked about the bonding, you know, between the two layer, and so that it's a ceramic, so that it'll break easily. Center it, and compared to other processes, metal processes is really fast. It's really fast when you look at the printing. When you add in the rest of the processing, it slows it down a little bit, but we're going to talk about that. So about 250K to get started. So this is on the low end of the metal spectrum. So it's more affordable for some applications. All right. So here's the case study for this, and I can tell you this is an EDM shop over in Farmington. So they were spending $250,000 a year in tooling from outside sources. They started using bound metal systems, so the desktop metal, one that we were just looking at, to build their fixtures and their tooling. So once again, every one of their EDM machines, and I think they have close to 100 of them, need metal fixtures and tooling. So they showed us a part that they made using the desktop metal system. It cost them, so it took them 3 days to print it. It took them 4 days to sinter it. So they had, I think it was a full 7 days processing time to build the fixture. They took it out of the machine. They had their shop either EDM it or machine it wherever it needed to be machined, or to put in inserts for, you know, cap holes or whatever. The total cost for them to do that themselves was $200. They were paid an outside company $1,200 to make that fixture. So that's $1,000 savings. Their return on investment was 9 months, the machine paid for itself. They were able, this isn't a good thing necessarily, but they were able to get rid of their tool maker. They helped him get another job. Tool makers are hard to come by, so he wasn't hurt by it. And now they're doing almost all of everything that they're building in-house, they're building with that piece of equipment, that added a piece of equipment. And so they still send out a little bit of stuff, but not much of anything. They also use polymer. They have a filament printer, a rise printer, and they have a resin from Form Labs to do their other kinds of fixtures. So they do CMM fixtures, and they do flow testing. They're creating holes, basically damaged holes and balls cutting off. So they do a lot of flow testing on the aerospace components. And so all those fixtures are built now using additive. All right, any questions on polymer? Here again, several companies available. There's some really cool things. I haven't been passing parts. No one passed. Oh no, we'll get to that. So these are parts that were made using a bound metal process. One of them is ceramic. I take that back. We're testing on what I'm talking about last second. All right, powder bed fusion. So that's the machine that we had downstairs that had the 10-inch cube. So that starts with a flat build plate. It spreads a thin layer, like 50 micron thick layer of powder, metal powder. It has a laser beam that gets steered by a mirror system, and it directly melts the laser powder. It drops, it screens another layer, melts it, drops, screens another layer. So when you get done, you have this box filled with metal powder and your parts are in the middle of it. So it's probably the prevalent technology in use today for building parts, metal parts, by many different people. This is a part we were talking about earlier. This is GE, but this is a meter wide part. So that's the state of the art right now. It's about a meter cube that they can build parts in. This shows it actually used. So here you can see where this is the first layer where the laser has melted the powder and the laser is going to finish up that metal. So these are some parts that we've done here. So this one in particular is this catalytic converter. That's where fuel cell company and here, but that has 750 micron holes that run the length of the part. They originally wanted us just to build a bunch of these and they were going to weld them together. So we said, why don't we just build this as a single piece? And so we built it as a single piece, and then all we had to do was weld the cap. We talked about casting replacements. These are a couple of pieces that normally were cast. This is for a company up in Enfield. So they needed, I don't know, half a dozen of these things to finish a customer order, and it was a 6-month lead time for their castings. There's probably other processes you can use, but we were able to hand them these parts in 2 days. And we did 25 of them. You can see the right to get back to this is a prototype. Anybody guess what that is? The prototype of? Ice cream scoop. So we work with all companies, all technologies. So anyway, but you can see here, a lot of times with this process, these are built directly on the plate. We have to heat them or use a bandsaw to cut them off. These, because of the shape of them, we had to build in support structure. So the cutting and removing that support structure, then blending in the surface can be issue. This is a great example of part consolidation. once again, just the fineness of the part that you can build. So this was normally multiple parts, but until it's a single part, you can see how fine the structure is. And then last but not least, this is insert for a mold. This has conformal cooling channels that run through these structures. So instead of just being able to drill holes where you can get line of sight with your drill and putting cooling holes in it, you can put the cooling channels inside exactly where you need them to be the most efficient at cooling. So that's that was built with that machine.
Thank you.
What kind of material, like
That's stainless.
stainless?
Yeah, here again, these machines, the metal machines that are designed to work with various materials like downstairs will inert, and we can run reactive or non-reactive materials in them. But once again, if you can weld it, you can buy powder. That's the other availability of material.
Are there certain machines like different material metals that like you need to buy this kind of machine for tool steel, this kind of machine for stainless?
They usually just break it down into reactive and non-reactive. So if it has an inner atmosphere, you can do anything in it. If it doesn't, you're probably limited to to steels and tool steels and stainless steels, non-reactive stuff. But if the machine's inert, you can literally run, depends on the machine, but you can run almost anything. So we have a machine downstairs. We've done everything from on the reactive side. So we do various aluminums, we do titaniums, up to tantalum. So, low melting point to refractories. We do steels, tool steel, stainless steel, nickel alloys, chromes.
Wow.
Just anything. We do a lot of stuff that you wouldn't normally try to be adequately,
Sure.
which is the fun part.
And you heat treat after?
Yes, so on a material basis or a metal basis, whatever you would do for afterwards, you can certainly do with it. It's a fully solid piece of metal. So if you heat treat it, if you dip it, heat treat it, you can certainly do that. Polish it. All right, another process is called binder jetting. And that works just like powder bed, except that instead of a laser beam or a heat source, it sprays in the adhesive called a binder. And so you end up with greenware, this is greenware, that then ends up in a sintering furnace. And then these are examples of the sintered part here in this little brother. For this. Once again, most of the sinter-based processes give you the equivalent of metal injection molding, so it's not necessarily fully solid. Some of them you can actually infiltrate with bronze, so there's some marine applications or that comes in really handy. And you can not only do metals, but you can typically do ceramics. That's the technology that the casting people are using to make molds with as well, sand molds. So once again, the idea, casting, if that's the way to go, that's fantastic. But if you need one or you need 6 or 10 of them, you don't need a mold to do that. You're direct printing it. So it gives you, gives you the ability to do that. The beauty of this too, the automotive industry started to embrace this technology. So right now, BMW and Volkswagen are starting to make production parts with this. The gun industry is using this. Once again, if you metal injection molding is used to make a million different things, but you need a mold. And so if you need a small quantity of parts, you do prototyping, you need a repair part built. This is a great technology for doing that kind of work. Okay, directed energy deposition. So this is another of the technologies that we have here. In this particular technology, what we're doing, we're starting with a build plate. And then a laser beam comes down, forms a melt pool, and we're blowing metal powder into it. And then it moves up, and we do another layer and another layer, until you end up with your finished part. So here again, you can see this is quite coarse. We make pretty big layers with this, so it's quite a coarse finish. So once again, some kind of post processing of surface finish is important. But that's a piece made from titanium, so it's a part that is it was I think a part of a tool that we made for somebody. Once again, I don't know, you have to explain that maybe. And once again, what would the dies cost in order to achieve that? So, so we have a number of different pieces of equipment. We're going to dig into a little bit more. So they're using it for new part builds. All these can be used for that. We do a lot of repair work with ours. One of the cool things with this technology is that we have multiple hoppers on the machine. So that means that we can spray different kinds of materials. And so you can do that, you can mix them together and help people develop new alloys. But you can also start with one material and then you can braid off to another material or switch between materials. So the idea of what's called a functional graded part, if I need heat resistance somewhere and abrasion resistance somewhere else, the possibility is there to do that. It would be very hard to do that on a commercial basis right now, as far as the quality control and the utility goes, but there's a lot of people that are looking at that as a potential process. Surface treatments and coating. So one of the earliest uses for this technology is cladding. So here again, this technology has been around for a long, long time. People do it in order to, once again, create a surface that's wear resistant, chemical resistant, heat resistant, whatever. And then here again, a lot of the concept behind this is the casting replacement, where this is faster than some of the other technologies. So it's kind of in the middle. So a part that we want a casting replacement. The metallurgy from this is casting, high-end casting or better. So we typically get raw quality from it. All right, so with additive, I can only build where I can get my heat source when I'm using a laser-based process, and I can only machine where I can get a tool into. But if I combine them both into a single machine, then I have a kick-butt machine called a hybrid machine. And so this is our DMG, and we'll now take a look at it. But this is the normal spindle up here. This has a 60 tool changer on it, and the head kind of folds off into a little garage to keep it out of the way. But you can switch back and forth between the technologies whenever you want to. So let's say we're building this part, which we'll get a look at. This has some sharp edges. So the engineer started that with a flat build plate. He added, created this trumpet section, turned it to mill turn machine. Then he used in full 5 axis, he added the fins back onto it, or added the fins onto it, and then he finished machining it. So that particular part, it was made from 316. That was under 5 hours from flat build plate to that level of finish. That was made hollow, it could be made solid. But so we think to make that with a conventional machine out of a block of 316, that's probably 10 or 12 hours. I'm not sure, but to do most of that's probably going to be roughing. With this, you're really doing one roughing cut and then doing the rest finishing. And so, the question is with 316, how many tools would you go through to rough machine it? And so how many with this is more of a question, how many of these can you build with a set of tools instead of how many tools do I need to build one? So anyway, so that's the Impala project. We've got some other things that we'll take a look at now. When we go. Which should show. So that's starting out, had started with the flat build plate that's building the trumpet section. Here again, the machine is full 5-axis, so it can do milling or additive in full 5-axis. And then that's obviously the turning. He's showing this being turned dry, but we can wet machine as well in that process. And then full 5-axis here again, adding the fins. Probably 80% of this machine would be in machinist. So it takes a lot more skill. And it's easier to learn the additive part of it than it is the machine.
That the latest and greatest in technology right there.
Yeah, for all intents and purposes. We've had the machine, this technology has been evolving as well.
That's amazing.
Yeah, and so we've had this for 6 years. So. But like I said, more and more companies are getting into it. But so some of the project that we worked on, here again, this is a 220-pound valve housing for the nuclear power industry. Once again, their problem is lead time. And so if they start to get cracks or cracking, you know, in a fitting like this, it can shut them down. And so for months, get into replacement. So this is a much quicker way of doing it. This was a project we did for NASA. So the space shuttle main engine is being used in the space launch system. That engine is made from 1980s technology and 1980s materials. The materials are far eclipsed what they had available to them then. So they're looking to do a totally additive manufactured engine within the next 10 years. So this is a liquid oxygen inducer for them. And then we talked about this is Air Force repair. And so, you know, we've added some bosses on here, but basically we'll be building some of the structure around there. We're doing, like I said, a lot of aerospace repair with our machines upstairs. And our other tool that we're going to take a look at is WAM. So wire arc additive manufacturing. Once again, the idea of building big is industry trend. So when you look at this, we have about a 6-foot square on top of the table that we can build in. And so the first project we're doing on this machine is with the Navy. We're doing the casting replacements. And so 250 to 500 pound structures. We can interchange heads. So this has a cold metal transfer similar to MIG, soft plasma similar to TIG, and then this is a laser wiring effect here. So we can switch heads to change the technology based on what we want to do with it. It's up and coming. When you look at its application in the industry, so this is GK on aerospace. So this was at Oak Ridge National Lab. I think they moved this. They got an additive center in Texas. They just moved this to. So they're using it primarily for airframe development. And this is from Relativity Space. So this makes rocket fuselages. So this will print a fuselage 24 feet in diameter by 120 feet long. And it'll take them a few months to do that, but it's much, much faster. And here again, they're consolidating thousands of parts into a single structure. From neat applications for it. Solid state processes. I don't have photos up there. Oh, I do have one on the next one. Friction stir additive manufacturing. You guys have heard of friction stir welding. So this is now, all right. So you basically, you take metal, I'll just say metal rod, and you push down and rotate it. The friction literally gets it hot enough to become plastic, and it welds it together. With friction stir additive, it's the same thing, but instead of welding plates together, it ends up building a layer. Just like the other additive technologies, you just build that up layer after layer. You get some amazing metallurgy with it, and you take a look at it, something else that they're doing with it. Cold spray is they're using similar powders to what we use, but they're accelerating them to 2 times the speed of sound or more. And the impact of the particles, they heat them up a little bit, but the impact of the particle fuses it into the layer underneath there. And then ultrasonic is literally using ultrasonic energy, and they use foils as a feedstock. And so it welds the part together using ultrasonic. So if we look at ultrasonic, this company Fabriconics does it. So this shows the foils back here, but this is a great tool for doing mixed materials. So they're doing a lot of work for like the satellite industry where they're doing heat pipes and heat exchangers, with copper for heat conduction and then corrosion resistant materials on the outside or whatever. This is a part that was made, that was with friction or with friction stirrer. This is a friction stirrer, so you can see the layers, very coarse, but it builds very quickly. So you're making near-net shaped parts and then finishing into your final shape. So these are some rings that they recently done. The world's largest metal 3D printer has been built and is being installed at I think it's being installed out at Rock Island Arsenal. And so they're going to be printing tank holes. So I mean, this machine is the size of this room out here in the lab, for giant structures. And shipbuilding, we actually use that. But the Department of Defense, aerospace, and the marine industry are very interested in that, both for building new parts, replacement parts, and for doing repairs like on the hull, or repairing the armor on a tank. So amazing technology. All right. Any questions about any of the stuff that we talked about? I'm running long. Okay. So we'll do very quickly go through the rest of this.
Joe, you had a question from the audience that
Yes,
I'm here
good.
to help ask.
Thank you.
You're very welcome. So Jason from the workplace, and anyone on the phone can also like unmute themselves and ask. But Jason, I'm going to ask this on your behalf. Are there accelerated training opportunities for additive throughout Connecticut?
The answer is we're working on it. So part of some of the programs that we're involved with is going to be doing more training. And so right now the answer is no, there really isn't. There may be some available at the tech schools from an introductory perspective, but there's not really anything that's more advanced that I'm aware of in the state, even at the university level at this time. So, well, so anyway, getting started. There's a whole bunch, this isn't meant for you to absorb, but there's a whole bunch of different questions that you really need to ask yourself when you get started. And to help you down select, how big is the parts I want to build with it? What kinds of materials are, how complex are they? How many do I want to build? What are the skills and abilities of the people I have on staff? And, selecting the machine, onboarding it, and then incorporating it into your quality system. You're going to use it with manufacturing. So there's a whole bunch of things that this is a whole nother conversation that we have to have with anybody that wants to have it. But like anything else, you want to start with the end in mind. So once again, you need to really figure out what it is that you want to do. And if it's just get introduced to it and see who's going to use it, then your $300 Envoy printer is an excellent choice. So when you are buying things outside of the filament printer, you want to make sure and understand the entire process, because sometimes the other things associated with the technology can be very expensive. As an example, in powder bed fusion, you are going to be using metal powders, so you have to have metal powders, brought into your EH&S program. You're going to need a sieving station. You're going to need respirators, you're gonna need a water collection vacuum cleaner. So there's a whole host of other costs outside of the cost of the printer by itself. Important to understand. Infrastructure and onboarding considerations, once again. Well, some of the technologies, there's really none to worry about, plugs in 110 volts. Others, you might need special ventilation, you might need, even with metals, you may be required to have a special fire system. So there's infrastructure things to be considered. Post-processing, on the plates that we showed you before, with ice cream scoops on it, there were support structures. So you have to be prepared to remove them from the build plate. So one of the things we learned quickly on is that our EDM machine at the time didn't have a big enough throw to put the plates in and cut them off well. So you want to make sure that you understand what you need to do in order to do that. Some of the stuff requires hand processing and blending and things like that. So you need to be aware of what process steps you need to go through to create a part, and then what you need to do in order to create a finished part. Two very different things. EH&S here again, there may not be an issue if you have a film printer. Most common materials you could print actually in a shop or a office environment. Some filament materials you need to have a ventilation system because it can produce toxic fumes. Some of them you're working with chemicals that you can get sensitized to in the resin printers, and so being aware of these aspects of it. Quality management, once again, if you're making fixtures and tooling, that's up to you guys how you do that. If you're trying to build end use parts, you're probably going to figure out with your quality people how to get it into your quality system. And then here again, we talked about staffing and skills briefly, but who's going to use it? Most companies that are successful with this have somebody that becomes their champion. So the company we talked about earlier over in Farmington that onboarded the found metal equipment, they had a champion. We had a guy that like you that did printing at home, understood the value of it, demonstrated that to his management. They ended up buying machines, for work, for him to do work stuff on. They've added the metal printer, so they've been very successful with it. But they have somebody that understands it and enjoys it and wants to do it. So understanding who those people are in your company can be very important. For skills and training, a lot of the skills and training you already have. So if you yourself or anybody that you on your staff already does CAD design, works with CAD programs. Somebody, if you're doing metals with some knowledge of welding, is beneficial. The flux cell is a robot, so having somebody with robot automation background can be important. So it really depends on what equipment and technology you're onboarding. But a lot of the skills are transferable. When we talked about the hybrid machine, like I said, literally 80% of it is being a machinist. The other 20% is learning enough about the additive part of it in order to effectively make the parts. All right, our resources. Any questions so far or any other questions? No? Okay. So once again, we talked about this at the very beginning, but for an industry 4.0 technology, Sear down here is the guy to go to. Additive, but both of our goals is to get technology in, work with manufacturers to help them understand it. We have state funding for small to mid-sized manufacturers to help do technology demonstrations. We can work with any size organization or company anywhere. We have money for grant programs that we're going to talk about. We're here to help you onboard it and be successful with it. We're developing training programs around it. So one of the things with my existing state program is we're going to be trying to bring in or be able to do some certified training in it. There's organizations out there that do that. So we're going to bring the resources here to do that. my program that I have from the state, the ATAP, the Technology Adoption Program, that's what we're just kind of finishing talking about. If you're interested and you guys don't have a 3D printer, or if you're interested and you have one and you want to try a different one, we have a quick start program. So we have 3 actually Mark IV printers that we'll loan to you for 6 weeks. So you can, we'll take it, we'll bring it to your company, we'll set it up for you, we'll train you how to use it. You guys are, you know, given free rein with it. In 6 weeks, we come back and pick it up. You need to buy the material for it, is what I'm saying. And so what that will give you an idea, like I said, number one, if you're interested in additive and you don't have a machine, this is certainly a great way to get introduced to it. If you have additive already, the Mark Forge, you know, here again has you know, the chopped carbon fiber, it has a couple of other plastic, it has a flexible material. And the machines that we have actually can do things like this. So this is nylon part, but this has carbon fiber filament underneath to it. So you can actually get really creative with it and produce some really robust tools and stuff with it. Assuming that all of that is successful, we have 2 programs right now for additive that are voucher programs, grant programs. One's for 20,000. That's ongoing right now. So it's a matching grant. So if you want to go out and buy your own 3D printer, you know, you need to apply for it. Once you've applied for it, you can go ahead and go ahead and do the purchase of it. But that's up to $20,000. So if you're buying a $10,000 printer, you can put in for 5. If you don't use it up on one purchase, you can continue to use it till it's used up. And then if you're looking for higher end equipment or more equipment, you want to buy multiple pieces. We have a $100,000 grant program that kicks off. It's competitive. It's a matching grant, and it starts in, we'll take applications in January and February. So you've got to do your homework between now and then. But we have 6 of those to award. Last time we did it, we had 16 companies apply, and we did 6 awards. So it looked out. Okay, we have other. Eileen is here to cover any questions, but we got other funding opportunities for the workforce and training. So if you have any questions about any of those, Eileen can fill you in on those.